Hello everyone and welcome to our today's class. It is our third and last lesson on the topic magnetic effect of an electric current. As it is our norm, let me commence by giving you the quote of the day, which states that if you sacrifice your health in order to make more wealth, then you will soon or later sacrifice the same wealth in order to get back your health. So we'll discuss that quote at the end of our class today. So today we are continuing with the applications or the uses of an electromagnet, and today we are looking at the working of a moving coil loudspeaker. So the moving coil loudspeaker is used to produce sound in radios, television sets and other audio systems. It works by the fact that a current carrying conductor experiences a force when put in a strong magnetic field. Then our moving coil loudspeaker, it consists of a powerful magnet. So this is our powerful magnet here. It consists of a very powerful magnet that produces radial magnetic field. Radial magnetic fields are those that are concentrated. They are concentrated together. Then it usually has a speech coil. This is what we are calling the speech coil. So remember, the speech coil is flexible, or it is free to vibrate depending with the kind of force that is acting on it. So a speech coil which is wound on a cylindrical former and positioned in the narrow gap between the poles of the magnet is free to move back and forth in the magnetic field. So this is our speech coil. It is located in between the poles of a magnet. So if this is the north pole, maybe then this should be the south pole, such that you attach the speech coil in between the magnetic field, such that it experiences a very strong magnetic field. And remember, this is our very powerful magnet, so it has very strong magnetic fields, of course, which will determine the amount of force that will be acting on the speech coil. Then we usually have a varying electric current whose frequency corresponds to the sound to be produced is passed through the speech coil. Now, since the radial field of the magnet cuts the turns of the coil at right angles, a maximum force acts on the coil, moving it according to the Flemings left-hand rule. So remember, if this is our north pole, then this is our south pole. Then it means the magnetic field will always be moving from the north pole towards the south pole. So we are placing the speech coil in such a position that it is perpendicular, or it is at right angles to the direction of the magnetic field, so that a maximum force will actually act on it. Now, since the current in the speech coil is varying, it means the coil experiences a force varying in magnitude and the direction of the frequency of the speech. Now, we usually have a diaphragm here, which is of course is free to vibrate. It vibrates at the same frequency of the current in the speech coil. Then the large masses of air in contact with the diaphragm is thus set into vibration, then producing the sound. So this is how a moving coil loudspeaker works. So remember, its work is just to produce the sound, or to amplify the sound that came from another device. So suppose these coil terminals are coming from maybe a microphone. So remember, in the microphone, we did say that a microphone usually has it also has a diaphragm, such that when a person speaks through the microphone, the sound waves of the person causes the diaphragm of the microphone to vibrate. As the diaphragm of the microphone vibrates, it is we also have a coil within the microphone, such that as the diaphragm of the microphone vibrates, it vibrates with the coil. The coil within, which is placed within a magnetic field in the microphone. Now remember that whenever a coil is vibrating at right angles to a magnetic field, then a current will always be induced. Now, the current that is induced is at the same frequency, or is varying at the same frequency with the sound that is being spoken through the microphone. So the induced current is the one that is flowing through these our coil terminals. So the current that has been induced into the microphone flows through the coil terminals, then comes through this particular our speech coil here. Now, whenever a current is flowing through a speech coil, then remember the speech coil is placed midway or in between a magnetic field, because if this is our north pole, then this should be our south pole. Then it means this region, there is a very strong magnetic field flowing from the north pole towards the south pole. So remember, when we have a conductor carrying current within a magnetic field, a force will always be acting on it. That is according to Fleming's left-hand rule, that if we have a conductor within a magnetic field, that whenever a current is flowing through a conductor that is placed within a magnetic field, then a force must act on that particular coil. Now, that force is coming as a result of, remember, this is our coil terminals. So these coils are carrying current from the microphone. Now remember, a current carrying conductor has a magnetic field around it. So the magnetic field caused by the current within this particular conductor interacts with the magnetic field of this powerful cylindrical magnet of ours here. So the interaction of the magnetic field of our cylindrical magnet and the magnetic field due to the conductor carrying current, that interaction of those two magnetic field, that is the magnetic field due to the cylindrical magnet and the magnetic field due to the conductor carrying current. So the interaction of those two magnetic field is what causes the is what produces a force that causes our speech coil here to vibrate. It vibrates within this particular magnetic field. So according to the Fleming's left-hand rule, that the thumb will always indicate the direction of motion of the coil. So suppose this was the north pole, then it means the magnetic field is moving from this direction downwards. Then suppose maybe the current was entering through this particular direction, then of course you can align your first finger along the direction of the magnetic field. Then you also align your second finger alongside the direction of the current. Then observe the direction of your thumb. The direction of your thumb will indicate the direction of motion of our conductor. So since the current that is induced from the microphone, or in this particular wires here, or in our speech coil here, is varying, because remember, when a person is speaking, the voice is also varying, meaning the sound waves produced are also varying. When the sound wave produced is varying, it means the diaphragm, the vibration of the diaphragm within the microphone is also varying. The varying of the diaphragm causes the coil terminals, or the coil within the microphone, to also vibrate. As it vibrates within a magnetic field, an EMF or an electric current is induced. So that varying electric current, which varies of course as the frequency of the sound that is produced through the microphone. So the varying electric current, as the varying electric current passes through the magnetic field due to the current within the conductor, interacts with the magnetic field of our cylindrical magnet, causing the speech coil to vibrate. Now remember that our speech coil here is also attached to our flexible diaphragm. So that means as our speech coil vibrates within this particular magnetic field, it also causes our diaphragm, our flexible diaphragm, to vibrate. So as the flexible diaphragm of course vibrates, it displaces the amount of air that is trapped in between here. Now remember, later on we'll be looking at a topic called sound. Then we'll see that sound is always produced whenever air is displaced, or whenever air is set into vibration. So when we set air into vibration, a sound is produced. So in summary, I've just said that when a person speaks through the microphone that is connected through the coil terminals, the sound waves of the microphone causes the diaphragm of the microphone to vibrate. As the diaphragm of the microphone vibrates, remember a coil is also attached to the diaphragm of the microphone. So as the diaphragm of the microphone vibrates, it causes the coil within the microphone to also vibrate. Then the coil is set in such a way that as it vibrates, it is vibrating within a magnetic field. Then whenever a conductor or the coil is vibrating within a magnetic field, a current is induced. So the current that is induced travels through the coil terminal. So that current travels up to our speech coils here. Now whenever a varying current is passing through our speech coils here, then remember our speech coil, we have placed it midway or perpendicular to a magnetic field, because this cylindrical magnet also has a magnetic field. So whenever a current is flowing through or passing through a conductor, according to the person who discovered magnetic field of an electric current, and if I can remember very well, he was a professor by the name Hans Ørsted. Hans Ørsted discovered that a conductor carrying current has a magnetic field around it. So the induced magnetic field within that particular conductor carrying current interacts with the magnetic field of our cylindrical magnet here. So the interaction of the magnetic field of the cylindrical magnet and the magnetic field produced due to the conductor carrying current causes the speech coil to vibrate. So as the speech coil vibrates, it also causes the diaphragm to vibrate, because remember the speech coil is attached to our flexible diaphragm. So as the speech coil vibrates, it causes the diaphragm to vibrate. Then as the diaphragm vibrates, remember there is air that is trapped in between this region. So as the diaphragm vibrates, it sets the air within this particular region into vibration. Then whenever air is vibrating, actually a sound is produced. So that is how a moving coil loudspeaker actually works or actually produces sound. Then next we look at a circuit breaker. So a circuit breaker is used to replace or to substitute a fuse. The advantage of a circuit breaker is that once it has been disconnected or once the excess current has flown through, you can actually reset it. But remember, for a fuse, once the fuse blows off, you have to replace it with a new one. But for a circuit breaker, you only need to reset it, but you don't have to replace it with a new one. So in modern domestic wiring, a circuit breaker and not a fuse often is used to protect electrical components from excessive flow of current. Now, when excess current flows through the circuit, increased magnetic power of the electromagnet opens the switch, thereby stopping the flow of the current. Then once the problem causing the excess current flow has been corrected, the switch is closed by mechanical means. So remember, this is connected to input terminals. So there is current flowing through this particular circuit here. Then of course this is our switch here. Then this is an electromagnet. So remember, when the current is flowing through this particular, when excess current flows through this particular electromagnet, it means this particular core, this can be a soft iron core which gets magnetized and demagnetized by electrical method. So remember, in the electrical method, when we were looking at methods of magnetizing a material, we did say that in the electrical method, you just take a conductor, usually a soft iron magnetic material or a soft iron core. Then you connect it in such a way that a solenoid or a coil, you just wind a coil or a wire around that particular magnetic material. Then that whenever a current is flowing through this particular solenoid that is winding this soft iron core, then the soft iron core becomes magnetized. So remember, this is also a magnetic material. So when excess current is flowing through this particular coil, this electromagnet or this coil becomes magnetized. Now, when the coil becomes magnetized, it means it can now attract any magnetic material close to it. So when this coil becomes magnetized, it attracts this magnetic material. Now, when this one is attracted on this particular soft iron core that has been magnetized, it means now the switch is actually open. Because remember, it is this part that is completing the circuit here. That is when the current comes through this particular bulb, it goes through this particular our magnetic material here, then it completes the circuit. But when excess current is flowing through this particular coil, this particular soft iron core gets magnetized, therefore it attracts this particular part, which is also a magnetic material. So when this part is attracted onto the magnetized soft iron core, it actually breaks the circuit, or the switch becomes opened, and therefore the current, the supply of the current dies off, or the circuit becomes open, and that is how we protect the appliances against huge currents which can cause an electric shock. So if you're asked to explain how a circuit breaker works, is that when excess current flows through this particular solenoid, the magnetic material, this magnetic material gets magnetized through the electrical method, thereby attracting this other magnetic material. So as this magnetic material is attracted onto the magnetized magnetic material, so as it gets attracted here, it breaks this circuit or it makes the switch to be open, thereby protecting our appliances by cutting the current off. Then we have said that the advantage of a circuit breaker over a fuse is that once the problem has been corrected, that is the problem that was causing the excess current has been corrected, you can simply reset the circuit breaker by taking this particular completing material that is completing our circuit. You just take it back mechanically, unlike for a fuse which blows off when excessive current flows through. So that means for the case of a fuse, you have to buy a new one. But for a circuit breaker, you just come and replace or reattach this part back to the switch. Then lastly, we look at an electric motor. Remember, we said that earlier on that an electric motor will always convert electrical energy into mechanical energy. So like in this case, an electric motor is converting an electrical energy into rotational kinetic energy. Remember, kinetic energy is a mechanical energy. Mechanical energy is usually divided into two major categories, that is potential energy, which is the energy at rest, and kinetic energy, which is the energy in motion. So an electric motor will convert electrical energy into mechanical energy, and in most cases we are talking of a type of mechanical energy which is called the kinetic energy. So an electric motor is a device that converts electrical energy to rotational kinetic energy. So an electric motor, a simple direct current electric motor, it consists of a coil of insulated wire ABC. So these are wire A, B, C, D, which can turn about a fixed axis and a strong curved permanent magnet to provide the radial magnetic field. So this is our permanent magnet. It provides us with concentrated or the radial fields. Then the coil, this is our coil A, B, C, D, or our wire. Then of course is connected to a cell or a source of power or current. Then we have a rheostat for varying the amount of current. Then it also has what we call the carbon brushes, and of course what we call the split rings, or sometimes we call them the commutators. To commutate is just to change position, so we'll see in its working. So the current enters and leaves the coil through a split copper ring called commutators, having the two halves P and Q. So this is our first half, then this is our second half, then these are our carbon brushes. So of course the carbon brushes are the ones that are connected to the source of power. Then the commutators will be interchanging positions in its working. Then Now, assuming that initially the coil is in a horizontal position, now when the current is switched on, it flows through the coil in the direction, in this particular direction. So remember, the current will always flow from the positive terminal towards the negative terminal. So when the current is flowing in this particular direction here, it flows through from D to C, then from B to A. Now, how will be the motion of the coil AB? So remember, if we apply the Fleming's left-hand rule, remember we said that for electric motors, we apply the Fleming's left-hand rule. But for electrical generators, we apply the Fleming's right-hand rule. So because this is an electric motor, so for motors, we apply Fleming's left-hand rule. So you just place your first finger in the direction of the magnetic field. So if this is my north pole, then this is the south pole. So it means the magnetic field is flowing in this particular direction. That is from the north pole towards the south pole. So you align your first finger along the direction of the magnetic field. So you place your first finger this way in such a way that it is pointing along the direction of the magnetic field. Then of course you place your second finger alongside the direction of the current. So if I place the current from B to C, the current is flowing from B to C, so I place my second finger in such a way that it is pointing downwards, that is towards the direction of the current. Then of course you observe your thumb. Then also be sure to strictly use the left hand, because if you use the right hand, the results are likely to be the reverse or will be different. So if we apply the Fleming's left hand rule, you hold your fingers mutually perpendicular to each other such that the angle between the thumb and the first finger is 90, and also the angle between the first finger and the second finger is 90, or right angles. Then you align your first finger along the direction of the magnetic field. That is, if this is the north pole, then I'll place my first finger pointing from the north pole towards the south pole, because the magnetic field always moves from the north pole towards the south pole. Then I place my first finger along the direction of the current. The current is flowing clearly. If this was the positive terminal, then the current is flowing in this particular direction. So from B towards A, the current is flowing downwards. So I place my first finger downwards. So clearly, as you can see, my thumb will be pointing upwards. So remember, the thumb will always point in the direction of the force, or where that particular coil will be displaced. So when the current is switched on, it flows through the coil in the direction shown. Then by Fleming's left hand rule, side AB of the coil experiences an upward force. So as we can see, the north pole, the first finger is pointing from the north pole towards the south pole, that is in the direction of the field. The second finger is pointing downwards, that is in the direction of the current. Then automatically the thumb is pointing upwards. So that gives you a clue that the side AB of the wire will be pushed upwards, or it will move in the upward direction. That is according to Fleming's left hand rule. So the side AB will be moving upwards. Let's see what will happen to side CD or DC. So if I apply the Fleming's left hand rule, I will place my first finger, of course, in the direction of the magnetic field. So just take your left hand and then hold the first three fingers mutually perpendicular, that is this way. Then place your first finger moving in this particular direction, that is towards the direction of the magnetic field. Then place your second finger in the direction of the current. Now remember, for the case of DC, the current is moving from D towards C. So you will place your second finger. Actually try it practically and see whether it is also working for you. Place your second finger pointing in that direction, that is in the direction of the current, because the current is flowing from D towards C. If you place your second finger pointing in this particular direction, then your first finger pointing in the direction of the magnetic field, because the magnetic field is flowing from the north pole towards the south pole, then you realize that your thumb is pointing downwards. I'm giving you time. Try it practically. Just take your left hand, then place your first three fingers mutually at right angles or perpendicular to each other, that is this way. Then align your hand in such a way that the first finger is pointing in the direction of the magnetic field. That is the first finger, place it along from the North Pole towards the South Pole. Then the second finger pointed from D towards C. Place it along the direction of the current. Then observe the direction of your thumb. Actually, I'm also trying it practically, and my thumb is pointing downward. So that gives you a clue that the side DC will move downwards, because the thumb will always indicate the direction of the force or the direction of the motion. So you are seeing that when the current passes through, we have seen that side AB will move upwards, while side DC or CD will move downwards. Now, that gives you a clue that the coil will be rotating. If DC moves downwards and AB moves upwards, actually the coil will rotate in this direction. The coil will rotate in the clockwise direction. So AB, we've said side AB will experience an upward force and CD will experience a downward force. Now, since the current in both sides is the same, it means the forces, that is the forces acting on AB and the forces acting on CD or DC, will be equal because they are being produced by the same current. So these two forces causes the coil to rotate in the clockwise direction until it reaches in the vertical position with the side AB and CD down. So when CD, we've seen from the Fleming's left-hand rule that the thumb will point down. Therefore, CD will move downwards while AB will move upwards. So the rotation will the rotation of the coil will be in this particular direction. So it will rotate in such a way that now A comes upward, then D comes downwards. Also B comes upwards, then C comes downwards. So remember, while in that position, it means this conductor here, our conductors here will be in between the gaps of our split rings. And remember, side BC and AD are moving perpendicular, or they are moving parallel to the magnetic field. Therefore, if the sides are moving parallel to the magnetic field, it means in that case no force will act on that particular conductor. Remember, a maximum force is only acts whenever the conductor cuts the magnetic field at right angles or at 90 degrees, as seen by side AB and side DC. So we've said that since the current in both the coils in both sides are the same, the forces are equal and opposite. So these forces causes the coil to rotate in the clockwise direction, or in this particular direction, until it reaches in its vertical position with the side AB up and CD down. So the CD moves down and of course AB up. While in that position, or while in the position where CD is downwards and AB is downwards, the brushes, that is our carbon brushes here, they touch the space between the two halves of the split rings or our commutators, therefore cutting off the current flowing in the coil. So remember, when the coil is upwards, it means now our carbon brushes are not connected to our coil here. So when they are not connected, it means the current that was flowing is actually cut off. That is when CD is down and when AB is up, actually this one is in between the spaces, between these split rings. Therefore, current is not flowing, so the current becomes 0. Then while in this position, the brushes touch the space, that is when AB is up and CD is down, the brushes touch the space between the two halves of the split rings, cutting off current flowing in the coil. Consequently, no force acts on the side AB and CD. But since the coil is in rotation, that is because the coil is rotating, its momentum carries it past this position, and the two split rings exchange the brushes. Now remember, in the next rotation, actually P, this side will be on Q and this other side will be attached on P. That is, they exchange, the brushes actually exchange the sides of the conductor. So since the coil is in rotation, its momentum carries it past this position, and the two split rings exchange the brushes. So as the brushes are also exchanged, remember the current was flowing from the positive terminal here, but now when you are exchanging these brushes, it means this side actually comes on this carbon brush. Therefore, it means the direction of the current within this particular conductor ABCD will also change, because the brushes have also exchanged the conductor. Therefore, it means that the direction of the current will also change, such that if the current, because AB will now be on this other side, it means now the current will be flowing from A towards B, then C towards D. So the direction of the current through the coil is reversed, and consequently the direction of the force on each side of the coil also changes. This process is called commutation. That is the process of exchanging the carbon brushes. To commutate is just to change positions. Therefore, side AB is now on the right hand side. That is in the second rotation. AB comes, replaces DC, and of course DC, it rotates in such a way that the DC now comes in the position of AB. So the side AB is now on the right hand side and CD is on the left hand side. That is in the second rotation. Since AB experiences a downward force, now when you apply the Fleming's left hand rule, the AB has come to the side of DC. Therefore, the AB will move downwards, while the CD, which has come to the side of AB, it will now move upwards. So since AB experiences a downward force and CD an upward force, it means the coil ABC will continue rotating in the clockwise direction as long as the current is flowing through it continuously. Then the speed of rotation of the coil increases with the increase in the strength of the current flowing through the coil. Now, if the terminals of the battery are interchanged, then the direction of the current will be reversed or reverses, and the direction of the rotation of the coil is also reversed. Since AD, that is the side AD, our side AD and BC, do not experience any force, because current in this side is parallel to the direction of the magnetic field. So remember, when the conductor is parallel to the magnetic field, no current is induced or no force applies on it. The force is only maximum when the coil is at right angles or is meeting at right angles or is perpendicular to the magnetic field. So there are ways in which you can also improve this electric DC motor. We can improve it by winding the coil on the soft iron core. So you can wind the coil on the soft iron core, because the soft iron core is easily magnetized and demagnetized. So 4 ways in which we can improve the working of electric DC motor is: 1, by winding the coil on the soft iron core, because the soft iron core becomes magnetized and concentrates its magnetic field in the coil. So this increases the force on the coil. Another way in which we can improve our electric motor is by increasing the number of turns of the rotating coil. We can increase the number of turns of the rotating coil. Then the third way is, of course, using a stronger magnet. So if we are using a stronger magnet, it means the magnetic field will also be stronger, therefore more force will be induced, and therefore the rotation of the conductor will also be faster. Then the last way is by multiplying the number of coils and commutator segments. So we can split these commutators to be very many. Maybe we split it into maybe 6 times, so such that the exchanging of the carbon brushes will also be faster. Like for this case, we have only split it only once, so we can split it even 4 times or 6 times. So in summary, we've said the 4 ways through which we can improve the working of the electric DC motor is: 1, by winding the coil on the soft iron core; 2, by increasing the number of turns of the rotating coil. 3, by using a stronger magnet. Then lastly, 4, by multiplying the number of coils and commutator segments. So that is what I could handle, but I'll also recommend that students look at the working of a moving coil meter and also the magnetic tape pickup or the head. So these two, they also work on the same principle. That is the principle of an electromagnet. So if you have understood all the applications that I've discussed, then I don't expect moving coil meter and magnetic tape to give you problems in explaining how they work. So what you need to know is that we usually have an electromagnet that is usually induced such that it can produce a force or some current respectively. So also try looking at the working of a moving coil meter and magnetic tape pickup, although the ones that I've handled are the ones that are most examined. So once you have understood those ones, you can apply that knowledge to the working of other devices, for example the moving coil meter and even magnetic tape pickup. So that marks the end of magnetic effect of an electric current. So since we've come to the end, so we need to discuss the quote of the day. The quote of the day stated that if you sacrifice your health in order to make more wealth, then you will soon or later sacrifice the same health, the same wealth in order to get back your health. What does that particular quote mean? So I'll give you an example. So for instance, sometimes we work extra hours in order to gain more wealth, to the extent that we deny ourselves time to rest and even time for taking a proper lunch. As a result, we end up eating fast foods, for example the chips, because we don't want to spend enough time on rest and eating a balanced diet. Now, it sounds funny, but when we get sick due to overworking our bodies, we usually go to the hospital and spend our wealth, that is in terms of paying the hospital bills, to get back our health. While in the hospital, the doctors usually recommend for you to be given a balanced diet and a bed rest, which are the same things that you ignored to give your body while at work because you are busy looking for more wealth. So actually it is a complete circle or a complete loop. So it's a high time that you start looking after your own particular health. You can always look for more wealth, but once health is lost, you cannot replace it. For example, when you lose a body part, it is difficult to replace it. So health is very much important than wealth. And also remember that our physical health is best taken care of through exercise and taking a balanced diet. And our mental health is best taken care of through meditation, showing gratitude and ensuring that you have the peace of mind. And lastly, remember that if you don't eat food as your medicine, you will soon or later eat your medicine as your food. Thank you very much. This is Kind Tuition Academy. Kindly do me a favor and hit that subscription button, and also remember to turn on the notification bell so that you'll be the first person to get a notification whenever I upload a new video. This is Kind Tuition Academy. Thank you until next time.